In this video, I'm going to focus on a different data set to illustrate Factorial ANOVA and provide a walkthrough of that. I'll also put this document on Canvas so that you can practice with the raw scores if you like. In fact, I encourage it. I'll also put some other several different data sets on for you to practice with because this is something we really want to get a lot of practice on. And then the second part of this particular video, I'm going to illustrate some problems where we have the summary table that's partially filled in, and I'll walk through the computations there. So here we have yet again a 2x2 factorial ANOVA. The previous one had psychotherapy and drugs. For this one, I'm just going to call it column and row. Column therapy could be anything you like, and row therapy. That way we get out of the habit of calling it psychotherapy and drugs all the time. And you know, this type of a design, this 2x2 factorial design, is probably the most commonly used experimental design in all of experimental psychology. And the reason for that is because you can test two independent variables simultaneously, which is a very efficient way to analyze data. And because larger designs where you have more than two variables, they get very complex very quickly, and it becomes very difficult to really have a handle cognitively, or I guess in terms of our ability to understand the meaning of what the interaction terms mean when we have multiple independent variables. The analysis of variance statistical procedure can accommodate unlimited number of independent variables. You can have hundreds of them, but there would be no way for us really to make sense of the interaction terms that evolve out of those hundreds of different independent variables. So one of the beautiful things about analysis of variance as a design feature is that it's economical in design. You can very efficiently see how different independent variables relate to each other. But the downside is that when the experimental designs get too large, it's really tough to figure out what is having an impact on what in terms of the interaction effects. So simplicity is a virtue here. Sometimes you will see 2x2x2 designs, three different independent variables, each having two levels, or maybe a 2x3 design, or even a 2x3x3. So those are all fairly common in terms of experimental design procedures that get published. Occasionally you'll see something that's larger, perhaps a 2x2x2x2. That's a 4 different independent variables, each having 2 different levels with it. And on that level, it's sort of stretching the mind's ability to understand what's going on. But we can still handle that, but that's about the limit in terms of the ability of researchers to actually implement these more complicated types of designs with numerous different cells. I mean, every different independent variable that you have magnifies the number of cells. So if this is a 2x2 design, we have 4 cells. It's literally the number 2 times the number 2 yields the number of cells that you have. If we had another independent variable, what we would have is a mirror image over here where the cursor is rotating that shows, let's say we have a third independent variable of sex of the participant, sex or gender, and so we have male and female. This side could be entirely male, but then we would have to have another panel that's entirely female, and so we would end up with 2x2x2, which yields 8 total cells. We would have these 4, but we would have another mirror image of that over here for females. And you can see how the number of cells that we have magnifies very quickly and each one of those cells, if you want to have decent statistical power, each one of those cells is going to need to have 30 or 40. Well, I guess I would say maybe 20 to 30 participants, and if you really want to have very high power statistically, 40 participants per cell would be very good. But it depends, the power of the test really depends on the magnitude of the treatment effects. So take that with a grain of salt. If you have treatment effects that are really very strong, you can see them with even something as small as this in terms of only having 5 people per cell. But that's unusual. It doesn't happen very much in real life. So at any rate, to get on with this example, we have column therapy and row therapy. And what we do first is, well, here's the table we need to set up. We need to calculate the, so in this practice problem, and again, I'll post this Word document to Canvas so that you have it. I say complete the table above, including the effect sizes, which are over here, and determine the correct critical value, which is right here, the F critical value, for the tests, and then try to draw a figure of the cell means, which I have not been able to do in class because normally I do this in class first. And since we're switching to online instruction as a result of the COVID-19 virus, then is it 19 or 9? At any rate, the novel coronavirus, we need to do things in a different manner. So I haven't yet done this. I haven't yet illustrated how to draw these figures. I guess I'll have a separate video on that. So going back to the data, what we want to do first is get the grand mean of all the cells. Here what you can see is that I've lined up the cells with the column means. 4.5 is the mean of column 1, that's these 10 participants. 2.5 is the mean of column 2, that's these 10 participants. 4.5 over here, the mean of these 10, and 2.5 the mean of these 10. And I just realized here that coincidentally these numbers match. I should probably come up with an example where they don't match. I also don't know why that's looking blurry to me. Maybe it's just my eyes. At any rate, the grand mean is 3.5. That's the mean of all the participants. Or if we take, so check this out, if you have exactly the same number of participants in each column, you can take 4.5 added to 2.5 and then divide by 2. So this number here, again, if you have equal number of people in each column, column 1 and column 2, this number 3.5 is going to be the midpoint right in between these two. It's got to be that way because this is literally the mean of this number and this number. It's also the mean of all of the participants, all the 20 participants in this data set. Okay, so now what we want to do next is compute the sum of squares between, and not shown here is the computation of the mean for each cell, but the mean of cell 1, where this is cell 1, is 5.4. We subtract the grand mean from it, 3.5, square that number, and then multiply it by 5. So what we're doing is we're not doing the columns and rows yet. We're doing the individual cells, and there are 5 people in this cell. That's cell 1. That's right here. And then moving on to cell 2, it's the mean of cell 2 is 3.6. I presume that's this one here. And we get the same number for cell 3. The cell numbers are right here in the margins. The upper right hand corner of each of the cells. That's cell 1, cell 2, cell 3, cell 4. And we take the mean of cell 3, which is this one, subtract the grand mean from it, square that, multiply by 5, and then do the same thing for cell 4. And when we add those up, when we do those computations, add them up, you get 40.20. And we'll run it in SPSS just to make sure that we have the right numbers. Next, we do the columns, and you can see that the number here changed from 5 to 10, and that's a reflection of the fact that when we're working with columns, we're working with the 10 people in that column. if we're working with cells, which is for the between group sum of squares, we have 5 people in that cell. But when we switch to the column and row main effects, then what we're looking at is the mean of all the people in that column or that row. And there are 10 people in the columns, 10 people in the rows. So that's where this number comes from. Then the mean of column 1 is 4.5. We see that here. Subtract 3.5, that's the grand mean. Square that number. And then move on to the next column, where the mean of column 2 is 2.5. That's right here. Subtract the grand mean, square that, multiply it by 10. And so let's see. 4.5 minus 3.5 is 1. When you square that, 1 squared is 1. 1 times 10 is 10. And that's where this comes from. Same thing over here. If you only have 2 of these, and if you have equal sample sizes, the number that you get on each side has to be equal. It's just the way that it works arithmetically. So that's sort of a handy little tool tip to know. But we can see the math here. 2.5 minus 3.5 is 1. Actually, in this case, it's negative 1. Square that number and we have 1. 1 times 10 is 10. And so that's where this number right here comes from. 10 plus 10 is 20. And then we move on to the rows, and we have the same pattern here with the sum of squares for the rows coming out to be 20. And we can start filling in the table. I've done it all at once rather than stepwise. But the first thing that we do, the very first thing would be this one. That's the between group sum of squares, which I calculated here. And not shown here is the total sum of squares. That lengthy procedure, if I had it on the page, would come out to be 51.00. 51 minus 40.2 gives us the within groups. Remember how these things relate to each other. I know there are a lot of moving parts at this point, but it's important to be able to follow this and understand how these different parts relate to each other. This number, let me see if I can highlight both of these. Yeah, so this number plus this number adds up to this number. That's the way that these work together. And that's the one-way ANOVA. That's the part that is related to the one-way ANOVA. The factorial ANOVA part is constituted by the columns, rows, and interaction. So we've calculated the columns here, and we've calculated the rows. Our 2 values for the columns and rows are both 20. Those go here. And the way that these 3 work, these 3 numbers all come out of this one. So 40.2 yields, when we break it out into its different components, yields 20, 20, and whatever this number is, which we don't know yet, even though it's on the page, but we haven't calculated it directly. We take the between group sum of squares, 40.2, subtract 20, and then subtract 20 again, and what we're left with is 0.20. So that's how I got that one. Now the degrees of freedom, remember that this is, the between groups is k minus 1, where k is the number of groups. We've got 4 groups, 1, 2, 3, 4. So this number has to be 3. The total degrees of freedom is n minus 1. We go back up here, we see that there are 20 people total in this experiment. So this number has to be 19. The within groups degrees of freedom is n minus k, where k is the number of groups, n is the number of people. So 20 minus 4 gives us 16. And also remember that the 3 of these are related, so that 3 plus 16 equals 19. The total sum of squares and the total degrees of freedom get divided up into the within groups and the between groups sum of squares and degrees of freedom. That's why they have this additive property. And then over here, the column degrees of freedom is c minus 1, this one. The row degrees of freedom is r minus 1. Well, looking at the figure, we can see that, well, there are 2 columns. There are 2 column means. So that number is 2 minus 1 is 1. Same thing for the rows. There are 2 rows, and so this number has to be 1. That's where I got these numbers from. And once you have these two numbers, and if you have this one up here, we know that this one has to be 1 because they have to, these three have to add up to this number up here. So 3 degrees of freedom for the treatment effect, which is the between group sum of squares. The treatment effect gets divided up into the columns, rows, and interaction. That's why we have the 3 up here being represented down here by 1 degree of freedom here, 1 here, and 1 here. If you know any two of these, then you can figure out the third one if you also have this. Then moving across these rows in the table, we take each one of these sum of squares divided by its degrees of freedom to get the mean square. 40.2 divided by 3 is 13.4. 20 divided by 1 is 20. 20 divided by 1 is 20. 0.2 divided by 1 is 0.2. 10.8 divided by 16 is 0.675. And I tend to refer to the within groups mean square as the key to the whole thing. That is to say, this is your error term. It's often called MSE, or mean square error. It's also referred to as MS within, or MSW. And sometimes it's just called error. It's the error term. In SPSS, that's what it's referred to as. But this is the noise. This is the noise in our signal-to-noise ratios, and we're going to have 4 different signal-to-noise ratios. Each one of these f-tests over here is a signal-to-noise ratio where we're taking the treatment effect. This one here on top is the overall treatment effect, and that is divided by 0.675. So let me see if I can get these highlighted just right. So 13.4 divided by 0.675 gives us 19.85. That's where this number over here comes from. And then for the next one, 20.2 divided by 0.675 gives us 29.63. And same thing here, it's the same set of numbers. 0.2 divided by 0.675 gives us a very small number, 0.296. And so then we need to compare each of these with its critical value. Now, I did not put an asterisk here. I probably should have. In fact, at some point I'll go back and add asterisks here because we can see that it's greater than the critical value. So where do these numbers come from? The critical values. Let's actually go to our table, and here I've got the. Let's see if I can move this around a little bit. Here I've got the table from the back of the book, from the back of the Welkowitz textbook, page 488. It's the F table. And what we need to do in order to use the F table is we need to locate our degrees of freedom. So for the first one, I want to show you how I got this number 3.24 for the F critical value. We have 3 degrees of freedom in the numerator and 16 in the denominator, so we need to match that up. Going to the the value of critical, the table of critical values at page 488, the F table. First of all, we want to use the 0.05 level. That's the one in standard type. The one in boldface is for 0.01. Well, maybe we need to use 0.01 because the F values that we have here are very, very large. You seldom see F values that are that large. So we need to cross-index these. We have the degrees of freedom in the numerator on top and the degrees of freedom in the denominator along the side here. So the columns represent numerator degrees of freedom. The rows represent denominator degrees of freedom. Well, we have, for the first one, 3 degrees of freedom in the numerator and 16 degrees of freedom in the denominator. So we need to match that up. We need to find that position within the table. And I'll show you how to do that. So here's 3. That's in the numerator. Right here it tells us it's the numerator. And then we need to find 16. But when I scroll down, I get to the end of the page and it only goes up to 13 degrees of freedom. Okay, so that's a problem because we need to have the exact value. I keep going on to the next page, which is page 489, And they've set this up a little bit weird because you can see that the degrees of freedom numerator go across here, stops at 12, and then the next page, yeah, they actually skip 13, but the next page starts with 14. So what they're doing is they're expanding the table in a direction that nobody ever uses, because this is a representation of the number of groups that we have. Go back to the thing here. Remember that this is the numerator degrees of freedom is k minus 1. So if we have 4 groups, then the numerator degrees of freedom has to be 3. What they're showing us here is a situation where we would have 15 groups, 15, and we lose 1 degree of freedom for the numerator degrees of freedom in the f-test. Well, nobody ever really does research with that many groups, so I don't know why this textbook has this page on here at all. They probably could have just gotten rid of it. So we're going to ignore this page because it has no relevance to any problem that we're ever going to do. We move on to the next page, page 490. And now we can see that it starts where the first page of this table stopped. So if I go back to the first page, we want 16 along the side, the 16 in the denominator degrees of freedom, and it stops at 13. So if I scroll past this page and hit the next one, we see that it picks up at 14. So now we have what we need. 3 degrees of freedom in the numerator, that's this one here, numerator degrees of freedom. 16 in the denominator, that's the ones along the side. And we match those up, and we see that we need 3.24 in order to be significant at the 0.05 level. Remember, at the very beginning, it says that 0.05 is in standard type, 0.01 is in boldface. So if our value is 3.24 or larger, then it will be considered significant at the 0.05 level. If our value is 5.29 or larger, it will be significant at the p equals 0.01 level or less. So we go back here and we see that, well, in fact, this number is really a lot larger than either of those two values. So we would say that this is significant at less than 0.01 level. So I actually do need to have 2 asterisks right here. And that's where this number comes. So that's the 0.05 level of significance. And we can see that this is much greater than the critical value. Now I've got a different critical value here, and the reason why is because we see that we have a single degree of freedom in the numerator for the columns, for the rows, and for the interaction, whereas the denominator degrees of freedom stays stable at 16. So we need to find that combination that is represented by 1 in the numerator and 16 in the denominator. I go back to my F critical table, and now I cross-index using 1 in the numerator right here, and cross-index that with 16, and it tells me 4.49 is the critical value for the 0.05 level. Let me get my document back up, and that's where these numbers come from right here. And they're all the same because they all have 1 degree of freedom in the numerator and 16 in the denominator. So this value here is common to all of them. But these 3 are going to have the same critical value because they have the same setup in terms of the degrees of freedom. So that's where those come from. And you can see that the interaction term is not significant. The omnibus F, or overall F test, is significant. The column treatment is significant. We call that a main effect, where main effect is a statistical term that's used to describe a single independent variable inside of a larger factorial ANOVA design. So the main effect for columns is significant. The main effect for rows is also significant. But the interaction of columns and rows is not. Now, interaction is never called a main effect. It's simply not done. We have 2 different main effects. Each independent variable has the ability to achieve a main effect status, and we call it a main effect really if it's significant. Although I guess there are times when people might say that the main effect was not significant. Normally people just refer to it as a main effect if it achieved significance statistically. excuse me, but the interaction effect is not called a main effect at all. The main effect is related to the independent variable. And the interaction is the interaction of these two different independent variables together. And then I've got these effect sizes over here. And the effect sizes that I calculate, I don't think I have the formula on this particular document. It's in the larger ANOVA document. This is the effect size R. You can see that that's, oops, you see that's indicated right here. Effect size R, where the formula for the effect size R for an F test is R equals the square root of F over F plus DF. DF within. So that would be, in this case, 29.63 divided by 29.63 plus 16, and then take the square root of that. I'll cover that in a separate video because I don't have that illustrated here. But that's how I got these numbers here. And then the other thing that I would say is that if you want to graph these things out, you end up with a graphic that looks like this, and you can do this easily in SPSS. And what we're looking at here is the columns. This is column 1, and this is column 2, and the rows, where the blue line is equal to row 1, and the green line is equal to row 2. The position that we're looking at right here, where we have column 1 cross-indexed with row 1, that number, if you carry it over here to the y-axis, that number is literally speaking, it's the mean of that cell. So that cell, if we go back up here, that's this set of people. I don't have the means displayed here, the cell means, but I presume that that cell mean is equal to 5.5 because that's what it looks like right here. I mean, that is literally the position, the circle here at the end of the line is the position that shows you the mean of this smaller group of people. And then for this group of people, this is the set of people who are in column 1, row 2. This represents column 1, row 2. And so we can identify them right here, column 1, and row 2 is in green. So that group is represented by the circle right here. The circle is the position of the mean of that group. So they must have a mean score of 3.5. And so that's how you read these things. What we're seeing here is the fact that we have a main effect for columns in the sense that the lines are going down when we shift from column 1 to column 2. That's the shift along here from column 1 to column 2. That's the main effect of columns, visually speaking. And then you can see the main effect for the rows because there's this big gulf in between these two rows. So the people who got, let's see, so whatever this treatment is, row therapy is present, that's row 1. So this is the row therapy present. Let's try to stop moving this around so much. Row therapy present versus row therapy absent. We can see that when we have the row therapy in place, the scores are greatly elevated relative to when the row therapy is absent. So that difference from here to here is representative of the fact that you have a main effect for rows. So again, when you shift from column 1 to column 2, when you see a pattern like that, that's indicative of having a column main effect. And when you see that these lines are separated from each other, that's indicative of a row main effect. And then the very last thing that I'll mention in this particular video is that if these lines appear to be more or less parallel with each other, that's a sign that you do not have an interaction effect. If you had an interaction effect, these lines would be very non-parallel. They don't have to cross. You can have significant interactions where graphically the lines do not cross with each other. That happens all the time. But it would be very, very difficult to have an interaction effect that's significant with lines that look like this, because they're not completely parallel, but they're almost parallel. So I think I'm at the about half-hour mark of this particular video, so I think it's a good place to stop. Maybe I'll pick up on this one later and add an SPSS computational or illustration of the SPSS computations for this particular data set. But I'll stop it here for now. So that's the second example of calculation of factorial ANOVA. Until next time, see you later.